Hello! In this video, we're going to prove the following theorem. Let n be an integer greater than 1, and let G be the set of equivalence classes of A, where A is an integer between 1 and n-1. Then G is a group under multiplication modulo n, if and only if n is prime. Now, first, let's remind ourselves, given any two integers A and B, we say A is congruent to B modulo n if n divides A minus B. And we have shown that congruence modulo n is an equivalence relation on the integers. So each integer has an equivalence class. And for each integer A, we denote the equivalence class of A like this. And at this point, we have defined how to multiply two equivalence classes. And the way we do so is we perform equivalence class of A times equivalence class of B is equal to equivalence class of AB for any two integers A and B. And we have shown that this operation is well defined. Now, we want to show that G is a group under this operation. And at this point, we have proven that U of n is a group under multiplication modulo n. U of n being the set of equivalence classes of A, where A is an integer such that greatest common divisor of A and n is equal to 1. Now, a property about equivalence classes that we're going to be using is A is congruent to B modulo n if and only if the equivalence classes of A and B are equal. And we're also going to be using some other preliminary results in proving this theorem. One of those preliminary results is the division algorithm. And it says given any two integers A and B, where B is greater than 0, then there exist integers Q and R, such that A is equal to BQ plus R, and 0 is less than or equal to R is less than B. And actually, these integers Q and R uniquely satisfy these conditions, but we're not going to need uniqueness to prove this theorem. Now, we're also going to be using some properties about prime numbers, which are the following. Suppose n is an integer greater than 1. Then n is prime if and only if the only positive divisors of n are 1 and n. N is not prime if and only if there exist integers A and B such that 1 is less than A is less than n, 1 is less than B is less than n, and n is equal to A times B. And a property about divisors that we're going to be using is the following. Suppose n is a positive integer. Then for all integers k, if k is a divisor of n, then k is less than or equal to n. In other words, this is telling us if n is a positive integer, then every divisor of n is less than or equal to n. Okay, so now let's get into proving this theorem. Now, we're trying to prove a statement containing if and only if. So to do that, we're going to prove if G is a group under multiplication modulo n, then n is prime. And we're going to prove if n is prime, then G is a group under multiplication modulo n. Let's first prove if n is prime, then G is a group under multiplication modulo n. To do that, suppose n is prime. From here, we want to show that G is a group under multiplication modulo n. Now, we know that U of n is a group under multiplication modulo n. So if we can show that G is equal to U of n, that will immediately tell us G is a group under multiplication modulo n. And to show that G is equal to U of n, we're going to show that G is a subset of U of n, and then we're going to show U of n is a subset of G. Let's start out by showing G is a subset of U of n. To do that, let's give ourselves an arbitrary element of G. I'll call it equivalence class of A. Well, then by definition of G, we have that A lies between 1 and n-1. And we want to show that the equivalence class of A is an element of U of n. And to do that, we would like to show that the greatest common divisor of A and n is equal to 1. And to see how we can show that, well, first of all, we know that the greatest common divisor of A and n is a divisor of both a and n. Now, the greatest common divisor of a and n is positive as well. So the greatest common divisor of a and n is a positive divisor of n. But remember, n is a prime number. So the only positive divisors of n are 1 and n. And that tells us that the greatest common divisor of a and n must be equal to either 1 or n. The claim is that greatest common divisor of a and n is equal to 1. So we're going to assume for a contradiction, we instead have that greatest common divisor of a and n is equal to n. So if the greatest common divisor of a and n is equal to n, well, since the greatest common divisor of a and n is a divisor of a, this implies that n is a divisor of a. But remember, since a is a positive integer, we know that all divisors of a are less than or equal to a. So in particular, n is less than or equal to a. But this contradicts the fact that a lies between 1 and n minus 1. Our assumption that the greatest common divisor of a and n is equal to n led us to a contradiction. So we must instead have the other option. We must have greatest common divisor of a and n is equal to 1. And this tells us that the equivalence class of A satisfies the requirement to be an element of U of n. So what we have shown here is, if we're given any element of G, then it follows that we're an element of U of n. So G is a subset of U of n. So now let's show that U of n is a subset of G. To do that, let's give ourselves an arbitrary element of U of n. I'll call it equivalence class of B this time. Well then, by definition of U of n, we get that the greatest common divisor of B and n is equal to 1. And now, we would like to show that the equivalence class of B lies in G. But it's not necessarily going to be the case that B lies between 1 and n minus 1, right? So instead of showing B lies between 1 and n minus 1, what we really want to show here is, we want to show that the equivalence class of B is equal to the equivalence class of some integer r, where r lies between 1 and n minus 1. If we can show this, then that tells us that the equivalence class of B is an element of G. So then how do we arrive at this? Well, this hints that we should use the division algorithm. So we are going to apply the division algorithm to B divided by n. So applying the division algorithm there, that tells us that there exist integers q and r such that B is equal to nq plus r, and r lies between 0 and n. Now the claim is that r is strictly greater than 0. And to see how this happens, we'll assume for a contradiction we instead have r is equal to 0. Well, if r is equal to 0, then B is equal to nq. And this tells us n divides B, and we know that n divides n, so we have that n divides n and n divides B, so n is a common divisor of B and n. So since n is a common divisor of B and n, but 1 is the greatest common divisor of B and n, we must have that n is less than or equal to 1. But this contradicts the fact that n is greater than 1. Our assumption that r is equal to 0 led us to a contradiction, so we must instead have the other option, r is strictly greater than 0. So then, this tells us we must have r is strictly greater than 0 and r is strictly less than n. And actually, since we're working with integers, to say that r is greater than 0 is equivalent to saying r is greater than or equal to 1. And since r is less than n, that implies r is less than or equal to n minus 1. And this tells us that the equivalence class of r satisfies the requirement to be an element of G. But the claim is that the equivalence class of B is equal to the equivalence class of R. And to see how that happens, let's note if we take this equation and subtract r to the other side, we get that b minus r is equal to n cubed. And this tells us that n divides b minus r. And from here, we have by definition of congruence modulo n that b is congruent to r modulo n. But then, from the property of equivalence classes that we were talking about earlier, this implies that the equivalence classes of b and r are equal. And we know that the equivalence class of r is an element of G, so this tells us that the equivalence class of b is an element of G. And so this shows if we're given any element of u of n, then we're an element of G. So u of n is a subset of G. And since we've shown G is a subset of u of n, and u of n is a subset of G, that allows us to conclude that G is equal to u of n. And from earlier, the reason why we said it suffices to show G is equal to u of n is because we know that u of n is a group under multiplication modulo n. And now that we know G is equal to u of n, that tells us G is a group under multiplication modulo n. So this proves if n is prime, then G is a group under multiplication modulo n. Now let's prove the other direction. We're going to prove if G is a group under multiplication modulo n, then n is prime. And to prove this direction, we're actually going to prove the contrapositive. We're going to prove if n is not prime, then G is not a group under multiplication modulo n. So let's suppose that n is not prime. Since n is not prime, then there exist integers a and b such that 1 is less than a is less than n, 1 is less than b is less than n, and n is equal to a times b. But these two inequalities tell us that the equivalence class of a and the equivalence class of b satisfy the requirements to be an element of G. Because we know that since a is greater than 1, we have a is greater than or equal to 1. Since a is less than n, that implies a is less than or equal to n minus 1. And similarly for b. So we have that the equivalence class of a and equivalence class of b are both elements of G. But the claim is that their product is not an element of G. If we can show that, then that tells us G is not closed under multiplication modulo n, and hence G is not a group under multiplication modulo n. So to prove that their product is not an element of G, assume for a contradiction, we instead have that their product is an element of G. Now, if we multiply equivalence class of A and equivalence class of B together, that gives us equivalence class of AB. But we know that AB is equal to n, so this is just the equivalence class of n. And when we add or subtract any multiple of n, then we still belong to the same equivalence class. So the equivalence class of n is equal to the equivalence class of 0. Another way you could verify this is we know to say that the equivalence class of n is equal to the equivalence class of 0 is equivalent to saying that n is congruent to 0 mod n. But by definition of congruence mod n, this is equivalent to saying n divides n minus 0, which is equivalent to saying n divides n, but we know that this is true. So since this is true, we can conclude that the equivalence class of n and equivalence class of 0 are equal to each other. So since the equivalence class of 0 is equal to the equivalence class of A times the equivalence class of B, that implies the equivalence class of 0 is an element of G. But what does it mean for the equivalence class of 0 to be an element of G? It means that the equivalence class of 0 is equal to the equivalence class of some integer where that integer lies between 1 and n minus 1. So we can say that the equivalence class of 0 is equal to the equivalence class of some integer k, where k lies between 1 and n minus 1. But since the equivalence class of 0 and the equivalence class of k are equal to each other, this tells us that k is congruent to 0 modulo n. But then this means n divides k minus 0, or in other words, n divides k. But k is a positive integer, so all of the divisors of k are less than or equal to k. So in particular, n is less than or equal to k. But this contradicts the fact that k lies between 1 and n-1. Our assumption that the equivalence class of A times the equivalence class of B is an element of G led us to a contradiction. So we must instead have that their product is not an element of G. So, under the assumption that n is not prime, we were able to find two elements of G, but their product is not an element of G. And that tells us G is not closed under multiplication modulo n. And since G is not closed under multiplication modulo n, there's no way that G could be a group under multiplication modulo n. And so we have shown if n is not prime, then G is not a group under multiplication modulo n. By the contrapositive, that tells us if G is a group under multiplication modulo n, then n is prime. So we have proven both directions of the if and only if. So this completes the proof. And so yeah, that's pretty much it for this video.